Today we are going to discuss the probability lesson under combined mathematics. This is the first video of the lesson. Normally, probability lesson is under combined mathematics 2, that means applied mathematics. From this lesson, for the A-level exam paper, in the combined mathematics 2 paper, there will be one question in part A. In the same paper, in the part B also, in a full question, as a part question, there will be one part from this lesson and the other part of the full question will be from statistics lesson. You might be already familiar with the probability because you are learning that in O-level also. Under the probability, first we have to discuss about random experiments. This is very important because throughout the entire lesson, only the experiment type we are going to discuss is random experiment. Random experiments have following common characteristics. The first one, the experiment can be repeated any number of times under the same conditions. That means we can repeat the experiment over and over again under the same condition without any problem. Second characteristic, all possible outcomes of the experiment are known before the experiment is carried out. That means we know all possible outcomes of the experiment before we conduct the experiment. The third characteristic, the next outcome of the experiment cannot be stated with certainty before the experiment is carried out. That means before the experiment is conducted, we won't be able to tell the next outcome with a certainty. We might be able to guess it, but we can't state that with a certainty. The fourth characteristic, when the experiment is repeated, a pattern cannot be recognized in the outcomes. In the first characteristic we discussed, we can repeat the experiment over and over, but even we repeat the experiment, we won't be able to recognize any pattern in the outcomes. We will discuss these characteristics using an example. The experiment of rolling an unbiased cubic die with its faces numbered from 1 to 6 and recording the number on the face that turns up. So it is clear we can repeat this experiment under the same conditions over and over again. That means first characteristic is here. All possible outcomes of the experiment are also known before the experiment is carried out. All possible outcomes are the numbers from 1 to 6. So the second characteristic is also here in the experiment. The next outcome we won't be able to state with a certainty. We can guess the outcome, but we can't state that with a certainty. So the third characteristic is also here. The final one, even when we repeat the experiment over and over, we won't be able to recognize any pattern in the outcomes. So the fourth characteristic is also here in this experiment. That means this is a random experiment. Next we have to discuss sample space and sample point. The set, which consists of all the possible outcomes of a random experiment, is known as its sample space. We know in a random experiments all the possible outcomes are known. So the set which consists of all the possible outcomes of a random experiment is known as its sample space. Normally it is denoted by capital S. An outcome of the experiment or an element of the sample space is known as a sample point. We know there are outcomes in a random experiment. An outcome is known as a sample point, or an element of the sample space. We know sample space is a set. So in a set there are elements. An element of the sample space, also known as sample point. We will discuss this using an example. Let's consider the random experiment of rolling an unbiased cubic die with its spaces numbered from 1 to 6 and recording the number on the face that turns up. So this is the same experiment we discussed in the earlier one also. We know outcomes are the numbers from 1 to 6. When we take all the outcomes as a set, that is the sample space. So you can see this is the sample space. We are using capital S to denote that. So each number here for each outcome or each element is known as sample point. So it is clear numbers from 1 to 6 are known as sample points. Here is another example. There are two identical cards such that capital R is written on one side and capital Y is written on the other side of a card. The cards are tossed simultaneously and the letters turn up are recorded. It is clear we can repeat this experiment over and over again under the same conditions. And we know all possible outcomes also. And even we can guess the next outcome, we won't be able to state the next outcome with a certainty. And even when we repeat this experiment over and over, we won't be able to recognize any pattern in the outcomes. So it is clear this is a random experiment. So getting capital R on both cards is denoted by capital RR, and getting capital R on one card and Y on the other card is denoted as capital RY. Accordingly, we can write the sample space like this. RR, so that means R on both cards. RY, that means R on the first card and Y on the second card. Here YR, that means Y on the first card, R on the second card. YY means both cards, Y is there. So you can see these are the all possible outcomes. That means this is the sample space. Each outcome here is a sample point. So RR, RY, YR, YY are sample points. So it is clear sample space in a random experiment is very important. So we have to represent the sample space. There are several methods to represent a sample space. First one, since sample space is a set, we can use the methods of representing a set to represent the sample space. These are the methods to represent a set. So we can use these methods to represent the sample space also. First one describing, then listing the elements using a Venn diagram, and the last one set builder method. We will discuss these using an example. Let's consider the random experiment of rolling an unbiased cubic die with its faces numbered from 1 to 6 and recording the number on the face that turns up. So we discussed this experiment earlier also. We can represent the sample space as a description. So the description will be counting numbers from 1 to 6. These are the all possible outcomes. Or we can list the element in the sample space. Normally the describing method we are not using most of the time. Second method is the one we are using most of the time, listing the elements. So the elements will be numbers from 1 to 6. So the third method, we can use a Venn diagram. So it is clear the sample space is a set of all possible outcomes in a random experiment. So The sample space will be the universal set. So we have to put the elements or the outcomes in the rectangle. So this is the third method, but we won't use this one most of the time. The last method, the set builder, we will describe the sample space using mathematical symbols and other methods. It is clear counting numbers are positive integers. So x, we will take x as an outcome. X is outcome or element. It is a positive integer. So we will give the range of the x values. So it is from 1 to 6. This is the set builder method. You are learning this one in set lesson also. This way also we can represent a sample space. This is also very important. We will use this method later also. So it is very important to remember this method also. Second method, using a grid. You might be already familiar with this one because grid you have learned in O level also. So we can use a grid to represent the sample space. Let's consider this example. Let's consider the random experiment of tossing an unbiased coin twice and recording the face that turns up. So we are tossing an unbiased coin twice and recording the face. So we can take the first try to the horizontal axis and the second try to the vertical axis. These are the outcomes of the first try. So we can get the head. H means the head, T means the tail. So H and T in the first try we can get those outcomes. Second try also we can get the H and T, that means head and tail. So you can see this cross represent an outcome. So that means here this outcome is representing first try we got head and second try also we got head. Like that we can represent crosses to represent outcomes in the sample space. This cross represent first try head, second try tail. Like that there are 4 outcomes. Using the grid also we can represent the sample space. So the advantage here, when the number of elements in the sample space is large, we can use this grid. But the disadvantage, only 2 tries we can put in the axis. If we have 3 tries or more than that, we won't be able to represent that using a grid. Third method, using a tree diagram. You might be already familiar with the tree diagram. We will be discussing this one later also. We will consider this example. Let's consider the random experiment of tossing an unbiased coin twice and recording the face that turns up. This is the earlier experiment we discussed. We can represent the sample space as a tree like the branches. So this is the first try. First try we can get H, that means head or tail. Here second try we can represent like this. These branches mean after getting the head on the first try, second try we can get head or tail. Here this means after getting the tail on the first try we can get head in the second try or tail in the second try. When we going along the branch, you can see the outcome is represented here. So the outcomes will be HH, HT, TH, TT. So you can see when we go around the branches, we will see the outcomes. So we will be discussing the tree diagram later. Now we will discuss types of sample spaces. First, discrete sample space versus continuous sample space. Discrete sample space. If the elements in the sample space are discrete, it is known as a discrete sample space. We will discuss this using an example. Let's consider the random experiment of counting the number of students of a class who are absent in a certain day. This class consists of 20 students in total. So here we are going to count the number of students who are absent in a certain day. So you can see we have 20 outcomes as the sample space. There can be one student absent, two or three, likewise until 20. Normally it is very rare to have a day that all the students are absent, but it can happen. So this is the sample space. So we can see the outcomes or the elements here are discrete. So these kind of sample spaces are known as discrete sample spaces. Continuous sample space. If the sample space is represented by a continuous number interval or several continuous number intervals, it is known as a continuous sample space. We will discuss this using an example. Let's consider the random experiment of measuring the lifetime of a light bulb. We are going to measure the lifetime of a light bulb in hours. It is clear as lifetime we can get decimal values also in hours. So we won't get any discrete values here. So we have to use a continuous number interval to represent this in the sample space. So we are using the set builder method for these kind of cases because it is easier to use that way and represent the sample space. So t is the time. So t is a real value. So we will assume the maximum lifetime of a light bulb is 2000 hours. So it can be 0 also. So the interval will be from 0 to 2000. So this is the way to represent the sample space easily. So it is clear we have used a number interval, a continuous number interval. So these kind of sample spaces are known as continuous sample spaces. So here is another type of sample spaces, finite sample space versus infinite sample space. Finite sample space. If the sample space consists of finite number of elements, it is known as a finite sample space. We will use this example to describe that. Let's consider the random experiment of drawing a bead from a bag which contains 2 black beads and 3 white. So all the beads are identical. So it is clear there are 5 outcomes we can get. We have 2 black beads. We will take B as black. So we can't write B and B because in a set we can't write the same element again and again. So we will take B1 for the first black bead, B2 for the second one, and W1 for the first white bead likewise. So you are familiar with this way. So we have represent the sample space. You can see we have 5 outcomes of 5 number of elements. So we have finite number of elements in the sample space. So those kind of sample spaces are known as finite sample spaces. Infinite sample space. If the sample space consists of infinite number of elements, it is known as an infinite sample space. There are 2 types of infinite sample spaces. First one, countable infinite sample space. If an infinite sample space consists of countable elements, it is known as a countable infinite sample space. Let's consider this example. Let's consider the random experiment of recording the face that turns up of an unbiased coin which is tossing up continuously until the head appears. So this is the experiment. We are going to toss an unbiased coin until we get the first head. So This is the way to represent the sample space. We can get the head in the first try. Here we can get the tail in the first try, but we can get the head in the second one. So we are going to stop there. Like that, here first two tries we are getting the tail, but in third one we are going to get the head. Likewise, you can see this is going to continue. So the number of elements here are infinite, but we can count the number of elements. So these kind of sample spaces are known as countable infinite sample spaces. So second type of infinite sample space is uncountable infinite sample space. If an infinite sample space consists of uncountable elements, it is known as an uncountable infinite sample space. We will use this example to describe this. Let's consider the random experiment of measuring the waiting time for a bus of a passenger at a certain bus stop. We are measuring the waiting time of a passenger until the bus arrives. So we are going to measure the waiting time in minutes. So it is clear we can have decimal values also in minutes. So we won't be able to represent this one in discrete values. We have to use an interval and we won't be able to count the outcomes here. So we have used the set builder method. T is the variable for time. T is a real positive value but can be 0 also. So the interval will be from 0 to 40. We have taken assumption here the maximum time the passenger have to wait until the bus arrive is 40 minutes. So it is clear we won't be able to count the outcomes and the sample space is also infinite. So these kind of sample spaces are known as uncountable infinite sample spaces. Now we will discuss about an event, a set which consists of one or several outcomes of a random experiment is known as an event. So an event is a subset of the sample space because sample space is the set which consists of all the outcomes. So the event is a subset of that. We will discuss this using this example. Let's consider the random experiment of rolling an unbiased tetrahedral die with its faces numbered from 1 to 4 and recording the number on the face which touches the table. So it is very clear this is the sample space. We can get the numbers from 1 to 4. So these are the set of all possible outcomes. So this is a sample space. So if we take the event of getting a prime number as capital A, these are the outcomes we can get for the event A. It is clear here only the prime numbers are 2 and 3. So capital A is clearly a subset of capital S. That means the capital A event is a subset of the sample space. Now we will discuss about different type of events: simple events, compound events, null events and complementary events. An event which consists of only one outcome is known as a simple event. An event which consists of more than one outcome is called a compound event. Compound events are also known as composite events. An event which does not consist any outcomes is known as a null event. If A is an event in the sample space of a random experiment, then the event that consists of all the outcomes of a sample space other than the outcomes of A is said to be complementary event of capital A. It's denoted by A dash. We will discuss these kind of events using this example. Let's consider the random experiment of rolling an unbiased cubic die with its faces numbered from 1 to 6 and recording the number on the face that turns up. Let capital A be the event of getting a multiple of 4, capital B be the event of getting a prime number, and capital C be the event of getting a number greater than 6. So you can see the sample space is the set we wrote here, the numbers from 1 to 6. A is the event of getting a multiple of 4. So you can see only one outcome is here from the sample space. B is the event of getting a prime number. So the prime numbers are 2, 3 and 5. So there are 3 outcomes. C is the event of getting a number greater than 6. So it is clear we won't be getting an outcome like that. So there are 3 events, only one outcome in A, so that is a simple event. B, there are 3 outcomes, that means more than one outcome, so a compound event. C, we don't have any outcomes there, so that is a null event. We are using this symbol to represent null event, or you can write like this. So if we take the A, we can write the complementary event of A as A, we have only 4 as the outcome, so the other outcomes will be there in the complementary event of A, that means A dash. So except for all other outcomes in the sample space will be there in the complementary event of A. So 1, 2, 3, 5 and 6. So in this video we discuss from random experiment to a event. So in the next video we will be discussing about more theories. So until then, have a nice day.